The next talk is 27 kilometers of fun about technology and hardware of particle accelerators. So let's see this.
All right, thank you. Prvi hoću da kažem da drago mi je biti ovdje sa vama. Ali dalje bolji na engleskom. So, I work at a physical research center, and the center is called DESI. And the place where I work is in the city of Hamburg. It's the second biggest city in Germany. And there we have quite a number of particle accelerators. And I work in science communication. That means I look at what the research is doing, and I try to explain it to the general public, like you people. And I try to make people better understand about physics and what is happening. So let me start with an invitation, because if you have a chance to come to the north of Germany, then it's a good opportunity to visit Hamburg, and you will be able to see all of these things that I put here on the pictures. We have some particle accelerators there. And one that is especially cool to see is the one on the upper right. This is called the HERA Accelerator. It is not in use today, but this means it is an opportunity for you to go and see it up close. It has a circumference of over 6 kilometers, and it is the largest accelerator in the world that is now easily accessible to visitors. So if you have a chance to come to Hamburg, then it will be a good opportunity to visit DESI. Today I will be talking about particle accelerators in general and some of the physics that we do, but mostly about the Large Hadron Collider, which is the accelerator in Switzerland, and it's the one with the 27 kilometers of fun. Much of the technology that I will be describing has also been developed at DESI, because it once, not today, but some time ago, it was one of the most important particle accelerator centers in the world. Okay, so I will talk about what we are doing and why we try to do this, to find out things about physics, naturally. And I will be describing some of the devices and the hardware that we use. And there is also an IT aspect to it, because as we will see, there is an enormous amount of data that is generated, and this data has to be collected and processed. So, what we are doing is we are using accelerators in the shape of a ring. We call them storage ring, and also in part some linear accelerators that make the particles go just in a straight line. And we give a high energy to the particles, which is the same as to say that we make them fast. But to say that we make them fast is only half the truth, because at some point, when you get close to the speed of light, then you cannot make the particle much faster, because the speed of light is the limit. But we can still increase the energy. We can double the energy, triple the energy, but still the speed will stay very close below the speed of light. So when we get to high energies, it makes more sense to speak of just the energy and not the actual speed. And well, when we have gotten them to a very large speed, we make them collide, and then we see what happens. And actually this see what happens is something that is very difficult, and it requires quite a bit of detector technology, and I will be talking also about that. So the basis of this kind of research that we are doing is this famous formula, which says that energy is actually the same as mass. But let me try to put it maybe in terms that are a bit closer to someone if you are tinkering with electronics. What if I say that parts, electric parts, electronic parts, are actually like the same as a device that you can build from them, and we might make it look like this. So the parts is really the same as the device. Well, okay, kind of, but not 100%. You have to put the parts together in the right way, otherwise the device will not work. And if you have the device, it's not the same as the parts, because the parts are put together. You connect them, and it's not the same as all the individual parts. So, the analogy works a little bit. So, if the mass can constitute something that we want to find out about, like, for example, the Higgs particle, then how about we just take the energy, and put it together in the right way, and we have a Higgs particle. Finished. Well, actually, it's not so easy, because we cannot assemble, we cannot just take energy and make the right thing out of it. There is no construction manual for the Higgs boson. So what we actually have to do is we have to create the energy in a very messy, in a very unprecise process, which is the collisions of particles. And it doesn't look like this, putting parts together nicely into a device. It rather looks like this. We make the collisions, and the result is lots of collision products. And out of all these collision products, we wonder, maybe there's inside the device or the Higgs particle that we are looking for. But it's a very hard job to find out from all these things that come out of a collision if there really is the right thing in there. And that's what you need a detector for. So we need the accelerator to make the particles fast. We need the collisions to convert the energy into something. And then we need the detector to find out if something has the thing that we are looking for. So these are the three things that we are using. And now I would like to tell you about the first part of this, about the accelerator and how it looks. So a storage ring, the first surprise, it's not actually a ring, so it's not a perfect circle. It always has some straight parts, and the straight parts are used to are the place where the particles actually get their energy. Now let's think about how we can give energy to a particle. We do it by using electric fields. But again, maybe we can find an idea that's a bit closer to our hearts. Imagine some kind of racing video game, and you have these booster arrows on the ground, right? You drive onto them and you get faster. We can do this with charged particles. Imagine an electron or a proton is like the little racing car in this game, and an electric field, if the polarity is correct, can be like a booster. So, okay, what do we do to make the particle really fast? Well, we just put a lot of boosters and and it will make the particle go really fast. Well, this would mean that we need a large electric field. How large? Well, really large. The energies that we want to give to the particles, like for example an electron, it would need an electric field of billions of volts, so gigavolts. And this is something that technically is not really possible to do. Because, you know, what generator do you need for a gigavolt? What connections do you need? What cables do you need for a gigavolt? It's not practically possible. So this is kind of a forbidden way. But what if we could do electric fields that are opposite to each other and put them in a row? Well, it would look like this. Okay, so here's our particle, and it gets a boost. But then the next field, it slows it down. So boost, slow down, nothing happens. But here's the trick. We can use alternating current, just alternating like you have from your power socket. And if we alternate it with the right frequency, then we can make it look to the particle like it's always on an accelerating path. So the particle is coming, and it sees the first accelerating field. The next one will slow it down. But when it gets to this point, we switch all the fields, polarity changes, and so the next thing that the particle sees is also an accelerating way. And in this way, from the point of view of the particle, it's always just accelerating. And what we do is actually we switch the fields. Now, this alternating current thing is not magic, you know, and like I said, the power socket has an alternating current of 50 Hertz, so the polarity changes 50 times a second. So we can think about what kind of frequency do we need to accelerate these electrons. Well, what we put in is that we have a device which is about 1.5 meters long. It's called the cavity. That is where the magic happens. So if the cavity is about 1.5 meters long, how fast is the electron going? Well, we know that, because electrons have a very, very small mass, and to make them go the speed of light, they just need a slight kick. So we give some energy to the electrons, and their speed will be almost the speed of light, and we can calculate with that. Okay, so it's 1.5 meters divided by the speed of light, and the result is a few nanoseconds. So every few nanoseconds, we must switch the field, because that's when the particle exits from one cavity to another. And so a field that changes every few nanoseconds has a frequency of gigahertz. And as we know, electrical fields on the order of gigahertz, also they are not magic. They are like microwaves, they are like wireless. Just that we need a little bit bigger of a device to generate the kind of fields that we are looking for. This is the cavity, like I said, about 1.5 meters long, and it is the device that we use to put inside this alternating electric field with the frequency of the gigahertz, and the electrons are rushing through it. Now, if we have a circle accelerator, then it's okay if we have just, well, maybe not one, but if we just have a handful of these devices, because the particles will come by lots of times, right? We put our acceleration here, and the particles go in a circle, and so they get an energy kick, and an energy kick, and an energy kick, and after a while, they will have been accelerated, and we don't need many hundreds of those, just a few, because they come by all the time. And so this thing is about 1.5 meters long. It's made of mostly of a metal that is called niobium. I had never heard of this before that, so niobium is the only thing I know. The only thing I know where they use niobium is for these cavities and some things in accelerators. The metal that we use needs to satisfy 3 conditions. You need to be able to put it into a shape, because as you can see, the shape is very special. It looks like donuts or something. And it needs to be this shape, so the electric field will fit in just right. And it cannot be too expensive, because we need a lot of it. And you need to be able to cool it down for superconducting temperature. Now, superconducting means that some metals, if you cool them down to a very low temperature, will lose their electrical resistance. So they will not be electrical energy converted into heat. And this is good, because with our large electric fields that change all the time, there are large currents flowing, and we don't want to heat up this thing because it might melt or something, so we just cool everything down. And it is cooled to a temperature of 4 kelvins, that is minus 269 degrees Celsius, so it's very cold. We use liquid helium to do this, and yes, that's how we do that. Now, the microwave, the gigahertz changing electric field, it needs to come from somewhere. We cannot just connect a household microwave, because it's not powerful enough. What we use is a device that is called a klystron, and a klystron can, well, they build them at different frequencies. The lower end is about 100 of megahertz, and it goes up to 2, sometimes even more than 2 gigahertz of frequencies. And we can see here that the power which they generate is around 300 kilowatts. That is just the power for the electric field which is used to drive the particles. And we don't just use one of those, we need 16 times 300 kilowatts for the fields that drive the particles. As a comparison, because this is, you know, something like a radio transmitter. We heard yesterday that to have a normal ham radio conversation from here to Japan, you need about 20 watts. I looked up the power that NASA uses to talk to spacecraft out by Pluto. They use about 20 kilowatts. And here we have 300 kilowatts to accelerate a few particles. So it's actually a large energy that we use. And at these high energies and at these high frequencies, it's actually better not to use cables. You know, you can make these kinds of signals go through a cable, but then you shouldn't let the cable lying around in a loop, or maybe the connectors will make a problem. So a better way to transport these radio waves or these microwaves is actually waveguides. And you can see it up here. It looks like it's for air, but it's actually not for transporting air. It's a hollow metal tube, and it's like a reflector. So I have this metal tube, and at one end I stick in an antenna, and the antenna transmits, and because there are the metal walls of the thing, the radiation gets reflected around, and it can only move in one direction, which is the direction of the waveguide. So to transport the energy, the fields from the klystron where it is generated to the actual accelerator, we use these waveguides, and inside the fields propagate. Okay, then we come to the second part, the actual circle part, which is the curves. So we have seen how the particles are accelerated, but if we just leave them alone, they just fly on in a straight line. But we want them to go in a circle. So what we need to do is to put there a magnetic field. A magnetic field, if a charged particle comes inside a magnetic field, it is put onto a curved path. So we need to put magnets at the right strength into the path of the particle. So a particle comes flying here, and there's a magnetic field, and then it will start to go around the curve. The thing is that we give the particles so much energy that they need very large magnetic fields to actually turn them. You cannot just use a small magnet because it will change the way of the particle too little. And so we have these, well, they're called cryodipoles, which means a very cold magnet. These are also cooled to about minus 270 degrees Celsius. And the LHC accelerator uses about 1,200 of them all around the ring part of the accelerator. Yeah, well, they are also expensive because you need the niobium and everything. So some estimates were that one of these things cost 500,000 Swiss francs. Yeah, so that's a lot of money. And to generate the field, we use a very large current. So it's an electromagnet, right? You have two conductors, and you put an electric current through them, and then in the middle there appears a magnetic field. And the magnetic field should have a strength of about 8.5 Tesla, because at a strength of 8.5 Tesla, it's enough for the protons that are going at this energy where we need them to just make the right angle around the curve. Well, and because that's a very large magnetic field, we need a very large electrical current, and it's about 2 kiloamperes, 12 kiloamperes, so 12,000 amperes. The power sockets, the power connection in your home, I think, at least in Germany, it will support about 16 amperes. And if you go above 16 amperes, then fuse blows out. So that's quite a bit bigger. And also, all around the Large Hadron Collider, 600 tons of this niobium metal is used to make the electrical conductors that we put the current through. And it's funny, I looked it up. The world production of niobium is not very much because, like I said, it's not used in very many applications. And it mostly comes from Brazil. And when they were building the Large Hadron Collider, they used a quarter of all the world production of niobium for 5 years. So they were like the biggest, the biggest customer for this sort of metal for a while. And well, so now we have these magnets, right? And we cool them down, so there's no electrical resistance. We put a large current through, and this gives us a large magnetic field, so the particles can go in a circle, and that's cool. But if the current is supposed to be constant, then there is a large energy stored. And this energy is actually extremely large. It's on the order of 10 gigajoules. And you can compare this energy that is just inside the magnetic fields, which we put there to be stable, is equivalent to the energy of a train with, well, 15,000 tons, you know, like a big freight train, moving at 150 kilometers. And if you imagine a big freight train moving at 150 kilometers, it could do a lot of damage if the energy is directed in a wrong way. So the magnets are also something that we need to watch very closely. We don't want the energy to, like the cooling to fail, and then a part of this energy could be converted into heat, and that would be very bad. And actually, we know that it would be very bad because one time it happened. The cooling at a connection between two of these dipole magnets did not work right. And so the superconductivity to the metal was lost. And suddenly, the large current was not just flowing through, but it was flowing through and generating heat. And this heat that was generated by the electric current made the liquid helium that we use to cool everything evaporate. So imagine that half a cubic liter of liquid helium suddenly becomes a gas. Well, it expands very quickly. And in this incident, it not only shifted the path of the accelerator for a little bit, it also filled about 100 or 200 meters of the tunnel with pure helium, just from the evaporation of the cooling. Which is one of the many reasons that whenever an accelerator is running, nobody is allowed near it. The tunnel is closed, the doors are closed, there is emergency shutdown if I try to open a door. You cannot even take the elevator to go down. Everybody needs to be away from the accelerator because these things can happen. It's not just about radiation and particles, it's also about lots of cold things and lots of magnetic energy. So, to put it together, we have this ring, which is not a perfect ring, but it's actually, you know, it has an accelerating part and a curved part. And together we use this to make the particles go in a circle and come by our accelerating portion every few times. Now, if you look at the layout of these actual machines, you will find that often they are connected. Some large accelerator is connected to some smaller accelerators. And these are called the pre-accelerators, because it's useful for us to put the particles not, you know, like energy zero, they are standing still, we put them in the accelerator and then turn it on. It's better if we give them some base energy, to say, and then put it in another accelerator which makes them at a higher energy. If you want to drive on the Autoput, you don't go there and stop on the Autoput and then accelerate, you know. You go before and there's a little lane, you match the speed of the other cars and then you join it. And this is how we like to do it with the particles also, because it gives us a chance to have a more smooth operation of the electric fields and the magnetic fields. And you can see this pattern also in the layout of some real-world accelerator centers. So this is the LHC. These are our 27 kilometers of fun. And as you can see, it is connected to many smaller machines. And also here, where I work at DESY, there was a connection of this. Now, it's almost like a historical evolution that all these smaller accelerators are connected to larger ones, because when all this acceleration business started, about in the 1950s, the machines were small, because you could find out a lot of interesting things with a small machine. But then we wanted to go to higher energies, because our machine had told us everything. So we built a bigger one, and we could connect the bigger one to the old smaller one. And this happened again and again, and oops. And as you can see here, there's at least 1, 2, 3 pre-accelerators to the LHC, which some years ago were the biggest machine, but then they became just the pre-accelerator for the next bigger machine. Okay, now we have all this acceleration. Everything is working great, and the particles are going really fast. And here comes the real business that we want to do, which is the collisions. The particles should collide, so we can find out something about what's inside or what can happen with the energy. It is very difficult, actually, to make the particles collide, because they're extremely small and extremely fast. So when we try to make collisions, we make a lot of them. And I will give you an overview and explanation of actually how many of them we generate. But first we need to take a look at what the beam looks like. So the stream of particles that we make go through the accelerator we call the beam. And actually, of course, there is 2 beams, because we need collisions. So a beam is not a continuous stream of particle, like you would, I don't know, from science fiction, a particle gun. They don't come out in a single stream. But they're also not single particles, like proton, proton, proton. But they are packed together in bunches. And the bunches might look like this. So we have a huge number of protons, and it slides through. And then there's a little pause, and then there's another huge bunch of protons. To make single particles collide is too hard. We cannot tune the magnetic fields that will determine the path to have one proton hit one other proton. It's impossible. If you calculate it, it's like trying to shoot with a rifle into the air, and somebody else also shoots their rifle into the air, and the bullets are supposed to meet in the air. But if I'm here and the other person is on Mars, so it's extremely difficult. So we have like large armies and everybody is shooting towards Mars, and then hopefully in the middle some of the bullets will collide. And the number of protons that we have in a bunch, like the number, the number of bullets that we shoot, it's 10 to the 11, so that's 100 billion particles in just one bunch. So large bunches are made to collide or are made to meet, and then hopefully among all these 200 billion protons that meet, there will be some collisions. So how many bunches are there? Well, they are spaced apart by 25 nanoseconds. So I'm standing next to the LHC when it's running, which is not allowed, but let's imagine. And here's a bunch, and I wait 25 nanoseconds, and then there's another bunch. And that means that they are apart by 7.5 meters. And about not quite 3,000 bunches are in there at the same time. And just a funny fact, because it's a lot of charged particles moving, it's actually like an electric current. But the electric current would look rather small, because even hundreds or a couple thousand of billion protons is actually not a lot of charge. So it's like 1.5 milliamperes as a current. But we don't want to, it's not a power cable, it's an accelerator, so that's okay. And to make them collide, well, we need to make these beams meet. And this is done at interaction points. So at these interaction points, we put special configurations of magnetic fields, we call them magnetic lenses, and we make the beams meet, we make them intersect. And so 100 billion protons in each bunch, and there is 2 bunches coming, one from each side. And the interaction point, the actual area where they meet, we make it as small as about a human hair is thick. So you take a human hair and you cut it, and the area that you get, if you look on, that is the area where we make these 200 billion protons meet. How many collisions are there when we do this? Well, about 10 to 20. And this is actually a bit too much for our instruments, but it's the number that we get. It's the number that we choose. Because if we make the number less, if we make it only 1 to 5 collisions, then we don't get enough data. This way we get a little bit too much data, but then we try to choose. We will look at how we deal with the data. So yeah, if there is more than 1 collision per bunch crossing, it's called a pileup, and it makes it harder on the detectors. So about 20 collisions, 1 collision per bunch crossing. And there are bunch crossings every 25 nanoseconds. So that means every second there are about 600 million collisions. So 600 million times per second, some proton collides with some other proton. And the experiments that we use to find out then what is happening there, well, this is just one part of one experiment. So keep in mind how large this is. We have here people and trucks, and it is this part in that experiment, and this is one of the 2 machines that we have there. And the actual collisions, the actual magic happens inside this tube. It's cut open here. So there's one stream of particles coming from the one side, and the other is coming from the other side, and the collisions happen right here in the middle. And then we put the detectors like an onion structure. Inside, on the very inside, next to the beam, is the most sensitive detector. And then come other instruments, and then it's the energy measurement. So we try to take very close to the beam. We want to know very precisely where everything is. And then further to the outside, we want to know how much energy there is. So the particles just smash into our detector components, and we can find out how much energy they had. So yeah, it's the inner tracking on the inside. We want to know where everything is. Because, of course, in the collisions, like I said, energy is converted into many particles. There can be 20, 30, 50 particles in just one collision, and we need to know where they're all going. So that's why we need the inner tracking. Then outside for the measurement of the energies is the calorimeter. This is Greek for measuring the energy. So the calorimeters, they actually stop the particles. And we can determine if we stop the particle, if we sort of catch it, we can determine how much energy it had by how much, well, damage it does to our detector. Not really damage, but still it's a process that changes the detector in some way. So some parts of these calorimeters you want to replace every few months or years. And then there is also another thing which is also like a calorimeter, but for the muons. Muons are a special part of particles, a special kind of particles that can also be generated, and they go through almost everything. They can go through a lot of lead, a lot of other materials. So the very largest part of the detectors is just for these muon particles, and we put them outside of everything else so they can catch the rest that didn't get stuck inside these other parts. Okay, so that's the instrumentation. And like this is a picture of the very inside of the detector. It's composed of small elements, and these elements can see if a particle went through. And well, we put enough of them, and we need to put in a circle because particles can go every way, and we want to catch them in every direction. So that's why these are arranged in a circle around the beamline. And then we need triggering, because let's think about how much data is actually generated. There are 40 million bunch crossings per second, and suppose that at every bunch crossing inside our detector, we want to know what is happening. So the detectors have a large number of channels. You know, a channel can be a voltage here. Every one of these small elements will have not just one, but many channels just for itself. So in all, in one of these big detectors, there might be about 100 million channels. And suppose that every channel has a data range of 1 kilobit. Yeah, let's say 1 kilobit or something. So it could be anything from like 0 millivolts to 1 volt in 1 millivolt steps. And then that will be about 1,000 bits. And that means that for every bunch crossing, we get about 1.5 megabytes of data. That doesn't sound so bad, but it happens every 25 nanoseconds. So the actual raw data that is generated all the time when everything is running is on the order of many terabytes per second. And, well, we cannot process terabytes per second. We cannot even store these terabytes per second. At least we couldn't do it for very long. So we need to pick some of the events. We don't record everything. From the 60 terabyte per second data stream, we just pick some things which are interesting. But it's very difficult to find out what is interesting. How do we choose? And this is done by something called a trigger. So the trigger is supposed to choose, oh yeah, this is about the reconstruction. So one event, right? We have the bunch crossing, and there's 20 events. And to calculate what happened in just one event takes the reconstruction of these experiments. So it's a couple million lines of C code that was especially written just for this experiment. And it has to simulate many objects because, of course, many things are meeting and many things are flying away. And so for every one single event, you would need about 15 seconds of real-time CPU. But with 600 million collisions per second, you don't have that much computing power. It's just not available. So, like I said, we need to pick certain events which are interesting to us. So what the trigger does, and most experiments use a several level trigger system, is where we tell the first level trigger, okay, you see an event, and now you have 25 nanoseconds of time before the next bunch crossing. You have this much time to find out if you think there is something interesting there. And if yes, you will put it on to the next computer or to the next trigger. And if not, just throw it away. And it will eliminate more than 99% of all the events, so we are left with a smaller data stream of about 100 or 200 gigabytes per second. But of course, this is still too much. The next level triggers have a bit more time to decide. They have 10 microseconds time to decide if that thing which they got from the first level trigger looks interesting or not, and if yes, they will pass it on. So then in the end, we are left with some 100 megabyte data stream per second, which is okay. We can manage that and store that. But then we still have to do all the calculations to reconstruct what actually happened in these events. And when we do that, we can get some nice, pretty looking graphics, which are like this. So this is a representation of what happened inside the detector at the very moment of this one collision. So here's a collision, and there's some particles flying outside, and some special particles flying further outside because they had larger energy. And there is also one here. And then if we look from another direction, it might look like this. So if we look into along the beam, it might look like this. And then the particle theorists come and they look at the data of this event and they will say, oh yes, I know this. That's what happened. And this then will be probably very interesting because there was a Higgs boson there. So out of everything that happened, goes into the detector, the data is picked and picked again, and then hopefully in the end, we will have some events like this that we can show to the theory people, and then the theory people hopefully will say, yep, that was a Higgs boson. So that's what we have to do. And to store all this data, because there's a lot of it generated, there's the LHC computing grid, which has a number of data centers around the world connected to each other. And these 4 experiments, they produce about 25 petabytes per year. And the LHC has been running for 3-4 years about. So already we have 100 petabytes of just stuff that we recorded happening inside the accelerator. I heard, now I'm not sure about this, maybe some of you know better, that this is among the biggest data collections that there is after the NSA data collection. And to distribute all this data and to store it efficiently, the dedicated data centers are connected with links that are about as large as gigabits per second to distribute the data. I have one story that I found from the time that the LHC was constructed. So they were thinking about what we should build. And this was about in the middle of the 90s. So they said, okay, we have this detector and it needs to collect the data, and we put it all together and we will put a 10 gigabit switch. But in the middle of the 90s, there were no 10 gigabit switches. So the financing committee said, well, you cannot plan to build a machine with a device that doesn't exist. And they said, well, but we asked some of the network people, and they said that when we finally get to putting everything together, there will be a 10 gigabit switch, so no problem. Well, they kind of managed to convince everyone to still put the money in, and luckily it happened, and there really were switches that were fast enough at the time that they were really putting it together 5 or maybe 10 years later. So sometimes you even have to plan ahead to use technologies that don't exist yet, because the whole process of thinking about it and planning it and finding the money and making the decisions is so long that technology has advanced a lot. Okay, now let's think about something, because we make the triggers choose what are the interesting events, right? And we want to find out about these very interesting events, but we have to find them in this enormous amount of data. And so if the trigger throws away everything that we tell it isn't relevant, well, we choose what's relevant, right? So what if in all this data that we throw away, there's something which would actually be interesting? We program it wrong, and then we don't find anything out that we wanted to know. And there is one great example from the 1930s about something like this actually happening. Of course, this was way before computers, but still, it's the same problem in principle. So this was when people used for particle detectors, they used photographic plates. You had a special kind of liquid or solid, and you put a magnetic field there, and then if particles go through, you will see it on an actual photograph. So you take it to a photography lab, and there's all the chemicals, and then you look at a physical photograph, and you say, ah, yes, there's a particle. So here in this photograph, we can see the important things are here. This is a metal plate, and this is the track of a particle that went through the metal plate. And we know that there's a magnetic field like this, which makes the particle not just fly straight, but actually to go on this curve. And we also know that the particle is coming from this direction, because when it hits the plate, it loses some energy, and then the curve gets tighter. So you see, first it's flying like this, and then it's flying more like this. And that means that it was coming from below, and it hit the plate, and then it's flying above. So this is like our event view. And because we know it's coming from this direction, we can calculate the amount of energy that it had and the amount of energy that it lost. And we found out that this has the mass of an electron, but from the direction of the magnetic field, we also know that it is positively charged. So we are actually seeing an electron, but not with a negative charge like they all have, but with a positive charge. So what's a positively charged electron, right? In the 1930s, they were thinking that this doesn't exist. You cannot have a positively charged electron. So some genius found a solution, and he said, well, the picture was just developed the wrong way around. If I turn it, it's an electron again. But of course, this wasn't the solution. This wasn't actually the case, because what they had actually found was a positron. A positron is an anti-electron. It's the antimatter counterpart to an electron. But they were not ready to accept this result, because he was thinking, well, it looks like an electron, but it has a positive charge, so there must be some mistake. When actually it was no mistake, it was just a positively charged electron. And only much later, well, a few months or years later, somebody did the experiments again, and they paid very close attention to all the magnetic fields and to all the directions and the currents, and then they were sure, well, there is no mistake in my instrument. It really is something like a positively charged electron. And then that was the discovery of the positron. And so that means only if you can accept something as a result, then you will be able to publish it. And well, so you need to kind of trick yourself, because if there's some result and you think it cannot be, well, maybe it can be. And that's what we call science. So with this very difficult process of accelerating everything, of making the collisions, of picking out the data, and then finally putting it all together in a theory, the LHC accelerator has already produced a large success story, because you see this gentleman here, which is Peter Higgs, and his colleague François Englert. They were honored with the Nobel Prize of Physics in the year 2013, after the LHC accelerator had announced that they had actually seen the Higgs particle. And the amazing thing is that the theory these two proposed actually was first thought of 50 years before. So it took 50 years from the ideas of these two, and actually a third guy, Robert Braut, but he didn't make it all the way. He died some years before this discovery. But Peter Higgs and François Englert, they lived to see long enough that this particle accelerator really confirmed their idea. And it was only possible because we were always building at the limit of our capabilities. Like I said, the 10 gigabit switch that they thought they needed in the middle of the 90s, but it didn't exist. These accelerators are always like the most advanced thing that we can build. And after 50 years, it was enough to confirm this theory. So that was a success. And so from the very start, where we say that energy is like the same as mass, like parts is a device, we can devise these machines to actually make the particles go in some packets, and then they collide, and there is a huge amount of energy. And if we pick everything right, and if we think the right way about the theories, then we can actually make some surprising discoveries. And the nice thing is that when the Nobel Prize was actually announced, it was not just these two men celebrating, but it was actually hundreds of people everywhere around the world. And even myself, I was sitting in Hamburg, we were watching live stream from Stockholm of the Nobel Prize. It was like a football game. And everybody was super excited when they announced that they had found the Higgs boson, and then later when they announced that there was the Nobel Prize given for this theory that was confirmed there. So it's a community work of everybody. It's not just the people who think of the theory, like the physical genius people. It is also those who construct the accelerator, those who put it together, those who program the software. It's a lot of people involved in this very big process. And it can be a lot of fun when you look at it, or when you are a part of it, or just to find out something about it, because it's like, yeah, it's cutting edge technology. And so with this, I would like to thank you very much for your attention, and I will be happy to take your questions.
Hi.
Hi.
How do you prevent particles that are going in opposite direction from colliding before you want them to collide, if you do it at all?
Yes, that's right. So we want the collisions to happen only in the collision points and not all the way around. So the LHC is actually composed of two accelerators. It is one pipe, and below that is another pipe, and they go in opposite directions. And only inside of the detectors, these two pipes, so actually, one pipe is going like this, and the other pipe is going like this, and they don't meet. But in the interaction points, we kind of open the pipes, and then there's an opening where we can direct with magnetic fields the particles to meet. And so we determine by the way that we construct the accelerator where the interaction points are, and that's where we build the detectors.
Okay, so I have a question about accelerating particles. You said that they move in a bunch, and that there are parts of that they are accelerated in that way that you're using alternating current, and some parts of the acceleration are changing.
The electric fields are changing.
The electric
yes.
fields are changing. How do you prevent? Well, if they are moving in a bunch, how do you prevent some particles from being slowed down and some from being accelerated?
Yes. So you need to. You're right. You need to synchronize your electric field with the way that the particles are actually moving. Because let's say I want the particles to be going along this way of the wave, but if they come too early, then they will not hit the right part of the electric field. Now it can happen, and it happens, that some particles are being slowed down, but then they are sort of pushed back into the next bunch. It's not a nice thing, but the thing kind of balances itself. When you have a bunch and some part of it is slowed down too much, then it will drift all the way back into the next bunch. And then hopefully there it will fit right in. But it's not nice, of course. You want to have nice and clean bunches. And so it's actually a lot of work to tune everything right, so that when the field is in a special position, the bunch will actually also be in the correct position. So yeah, that's a difficult thing to do. You're right.
Thank you.
I have two questions. One is very personal. Do you feel pain in your chest when you have to oversimplify a complicated process when you talk to general population? And second question is, how do magnets work?
How do magnets work? That's too difficult a question.
That was a joke.
Well, yes, you are right, of course. The presentation is much simplified from like one guy building the actual accelerator, presenting it to a bunch of particle physics people. There is almost no formula in this presentation. But I think that if you want people to feel like they learned something about an accelerator, it's better to first propose or to first present the simple principles, and then later, if they want to, you can look at all the formula. It's all public, you know, you can look at the data. But if I start with integrals and differentials and volume integration and everything, then I think people can lose interest. And so I don't mean to offend people when I give very simple explanations. It's just a way that I think it's good to start into the topic. And if you know already more, then that's great. And you can visit presentations maybe at universities, you can read documents on the internet, you can read books about particle physics. And I think that I would like to give a start into this process.
Thank you. Thank you.
As electrons, for example, repel each other, how do you keep them in a bunch?
Ah, yeah, good question. So we have 10 billion or 100 billion electrons in this bunch, right? And we want to make the bunch go through the accelerator. But they all have the same electric charge. They are all charged negatively, so they repel each other. So the bunch actually will not stay in a bunch, it will want to drift apart. And that's bad because our tube where the particles are actually going is only about this big. So if the bunch drifts apart, all the particles will smash into the wall and be lost from the reaction. So what we do is we have magnets called quadrupoles. They are not just North Pole and South Pole, but they're north, south, another north, and another south. And the magnetic field that is created between these poles is called a quadrupole field. And you can use it like a lens, like the lenses on glasses can focus the light. These quadrupole lenses can, in a similar way, also focus the path of the electrons. So I put a quadrupole magnet here, and here comes my bunch, and it's drifting apart, but then the quadrupole magnet makes it go together again. And so all along the path, we need lots of quadrupole magnets to actually push the particles together, even though their charge wants to kind of make them repel each other. All right, well, thank you everybody, and have a fun conference.